Okay guys, for example number 4, what we're going to do is find the extreme values of f of x, which is 1 over the square root of 4 minus x squared. And so in order to do that, we need to find the critical points, and we're referring to the x values. So we always look at the domain from a to b, so there's usually an interval of what x can be, and we go from a to b. That's the first point, or points. We look for a critical point. The next step would be to look at f prime when it equals 0, and then sometimes we look at f prime where it does not exist. Actually, we do that every time. And so if you notice, Mr. Adams wrote down a backwards E. That's symbolic language for there exist, and when I put a slash through it, it means does not exist. So to find the extreme values for f of x, we're going to look at the interval of the domain from a to b, where it's continuous, and then we're going to look at f prime equals 0 and where f prime does not exist. So the first step in this process is to graph this on our graphing calculator. And when I do that, it kind of looks like a smiley face or a smile. Now, truthfully, just to kind of jump ahead, this has vertical asymptotes at plus or minus 2. And our calculator simply cannot graph the way that we want to based on the limitations of the calculator. And we'll talk about that later. And so once we've but clearly by looking at the graph, x is between -2 and 2. So our interval x equals -2 and x equals 2, those are the two endpoints that we're going to look at later. And that just comes from the fact that 4 minus x squared, and then when we take the square root of that, it has to be greater than 0, because remember, we can't take the square root of a negative number. So I kind of wrote this down incorrectly on the board, but what we're thinking in our mind is that we can't have 0 in the denominator and we can't take a negative square root. And so, actually no, now I take that back, I did write it correctly. So anyways, if I go through the algebraic process of setting that equal to 0, we get that x can equal plus or minus 2. But when it comes to the inequality of this, we have to determine, like is for x less than 2 or greater than -2. And then to do that, I really just need to plug that into the graphing calculator. So I'm just going to graph the function, the square root of the quantity 4 minus x squared, and just take a quick look at the graph. There's a lot of things we could do. We could do some test by values greater than or less than -2, and the same for +2. But by graphing it, we can see that it's positive when x is greater than -2, and it's positive when x is less than 2. That little green line is positive when x is trapped between -2 and 2. So we know that, and that kind of helps us to determine what the relative domain of f of x is based on this limitation or restriction of f of x. Now we're only dealing with f of x. We are still on the first step, trying to find the relative domain. Remember, the question is the extreme value. So we want to find any minimum or maximum values, and then we look to see what the highest minimum value or the lowest minimum value and the highest maximum value are. And the first step in that is to find the critical points. And what we just did is we looked at the relative domain, which is from -2 to 2. Now, if you're wondering why my the recording of me is going really fast, I sped this up. We actually took 2 days in class to go through this example problem. There were a lot of questions in class that we answered, hopefully, and it really boiled down to algebraic concepts and just kind of reaffirming some of the steps that we did. And so by looking at this, we've completed step 1. We've found the relative domain of the function. Then the next step would be to find f prime. And so I guess that would be the next step for right now. We're supposed to, normally when we find the critical points, we're supposed to plug those back into the original function f of x. However, the reason that these are the boundaries of f of x is because it's where f of x is undefined. So we found the critical points, but they don't yield a minimum or a maximum value. Now that only occurs when your end behaviors or the behavior of the functions have well, in this case we have two vertical asymptotes, which means the function horizontally is bound, and so that means that the y values either approach positive or negative infinity, and we'll look at that later. We look at the calculator, and it doesn't necessarily show that in the calculator, but I'll prove that in a second. So then the next step would be is to take our original function f of x and then solve for f prime and then set that equal to 0 and find the zeros of f of x. And I think what we want to do is maybe review what we're talking about. So when we look at a function, okay, we are looking at the boundaries from a to b. Now some functions, like this function, already has a boundary based on what the function is, but sometimes they're bound back from a to b. And so even though there may be relative mins and maxes, you can see by the graph that I've drawn here that the endpoints could certainly be a minimum value or a maximum value. In other words, if I have a graph where the curve goes beyond the boundaries from a to b, I could have an extreme minimum or maximum that doesn't occur when f prime is 0. So that's why we always include those endpoints. It doesn't mention it in the textbook, but that's why we should include it, because we could have a minimum or maximum y value. So remember that when I say critical points, we're talking about the x values, and when we say minimum or maximums, we're talking about the corresponding y values. So we find the x's, plug them into the original function, and then from there we go and we try to find the corresponding y value. So step number 2 is to find f prime of this thing. So remember that f of x is equal to 1 over the square root of 4 minus x squared. And so I'm going to think of this as the quantity 4 minus x squared raised to the negative 1/2. If I apply the power rule to this, I'm going to toss the negative 1/2 to the front. Then the stuff on the inside remains the same. I'm going to take negative 1/2 and subtract 1 from it, which becomes negative 3/2. And then I'm going to tack on the derivative of the stuff on the inside. So negative x squared has a derivative of negative 2x. And the derivative of 4 is just 0, so I don't need to write that down. So this is basically the power rule with the chain rule tacked onto it. Just a kind of quick review, when we do the power rule, we're just going to take the power, which is negative 1/2, toss that to the front, and then the power, which is negative 1/2, we're going to subtract 1 from it, which you could think of it as subtracting negative 2 over 2, and so that's how we get the power of negative 3/2. You could leave it written like this if you want to, or you could toss that down to the bottom of the fraction so that you have a positive. But anyways, the 2's cancels and the negative cancels, so my actual slope is x times the quantity 4 minus x squared raised to the negative 3/2. I am going to go ahead, I think, and write this down with a power, a positive exponent power. And so remember that I could take that 3/2 and toss it down to the bottom, which translates as 4 minus x squared raised to the 3rd power, and then we take the root index of 2. So just a quick reminder that that's the same as x over 4 minus x raised to the 3/2, where the 3 represents the power of the base and the 2 represents the root index. Okay, and so we're putting that down on the bottom. Now the reason I did that is so that we could actually see. Remember that with rational expressions we cannot have 0 in the denominator, so that's a restriction on our domain of f prime. Now we got to remember that f prime is completely different than f. And so we're at the step where we set this equal to 0, and we're going to try to find the zeros of this. Now another way we could write that is the entire quantity of the square root of the quantity 4 minus x squared raised to the 3rd power. And so if we leave it like that, sometimes it's easier to manipulate. Well, now how do we solve this for 0? Well, clearly, if x equals 0, then I have a 0 in the numerator. And so x equals 0. And then the other way to solve this is I could think of 0 over 1 and set it equal to my expression and then cross multiply. And then you could see here also that x equals 0. So x equals 0 is the 0. All right, so we have some critical points, negative 2, 0, and 2. Now the last thing that we need to consider for our minimum and maximum values in the process. First was the boundaries. Second was the zeros of f prime, and then when f prime doesn't exist. Well, if you look at that problem, f prime doesn't exist when the denominator equals 0, which is basically the same scenario as f. So f prime and f are undefined when x equals 2 and negative 2. And so just to kind of recap what we're doing, when we go to find the extreme values of any function, the first thing we do is consider the domain, the closed interval that we're looking at, and we found those values to be negative 2 and 2. And then the next step would be to find the zeros for f prime. And then the third step would be to find where f prime does not exist. So step 2 is f prime of x is equal to 0, when we're thinking of the x values of f prime. And when we did that yesterday, or not yesterday, but today, because I'm taking 2 days worth of stuff and editing it together. And so when we went through that process, we found that x equals 0 is one solution to that. So, and then the other solution, which were undefined, were negative 2 and 2. And then we're looking for the x values for the critical points, and then we have to plug those values back into f to get the corresponding y values. And so the third step in that process, as I said before, was to find when f prime does not exist. And so I would say f prime of x does not exist. And I'm going to save myself a little grief by taking a backwards e, which means there exists, and putting a slash through it, which means where f prime does not exist. And we figured out that that would be 2 and negative 2, right? And so now I have 3 critical points, and I'm supposed to plug these into the original function, and then I'm gonna look at the corresponding y values and determine which one is the minimum value, which one is the maximum value, and then I'll have my answers algebraically. Now clearly, if I graph this in the calculator, I could figure that out rather quickly, but that's not what I'm trying to teach you here. I'm trying to teach you how to find it mathematically, numerically. And so I'm supposed to evaluate the original function f at 0, negative 2, and 2. And so if I evaluate this function at 0, I get 1 over 4 minus 0 squared, and that reduces down to 1 over the square root of 4, which reduces down to 1 over 2. Now you might ask, well, when you take the square root of a number, do you consider plus or minus? Again, you could look at the graph to determine that, but in most cases we always consider the principal root. Probably in this scenario, I would just double check the graph to make sure. And we will do that at the end. Next step, I want to plug in negative 2. But the problem with plugging in 2 and negative 2 is that my zeros in the denominator. And so that's undefined. So really, we're trying to find places where the critical points might give us information, but they don't always yield any positive results. So in this scenario, 2 of the 3 critical points were undefined. And so we'll deal with that in a second. So right now we know that there is either a minimum or a maximum at 1/2, and when x equals 0, then y equals 1/2. And we'll come back to that, and I'll show you a fancy algebra way to determine if it's a minimum or max in a little bit. But for right now today, we're going to graph it. Where x equals negative 2 and 2, it's really no help. So there we're going to have to refer to the graph. Here we basically have to determine if a function is defined. If so, what does it approach? And in most cases, because this has a vertical asymptote, it'll approach either positive or negative infinity in the y direction. And which is weird, because when we graphed it on the calculator, it didn't appear to do so. So what I'm going to do is I'm going to go into my calculator. I have to turn off my stat plots, and we'll go back to the functions. And let me turn that on, and we'll graph that. And I have to adjust my window, and I think I can enter it in manually, and as you see here, it looks like a little bit of a smiley face. Well, now I said that we have vertical asymptotes at -2 and 2. Normally when you have a vertical asymptote, the closer you get to the asymptote, the y value still keeps growing or shrinking. In this situation, your graphing calculator has some limitations. And so an interesting thing takes place that when I get really close to 2, so I'm going to manually plug in 1.999, and what you'll see is I'll get a corresponding y value. However, it does appear based on the graph that there isn't a y value. So the red numbers don't lie. My y value at 1.99 is 5.006. In other words, when x is 1.99, my y value is 5.006, which is defined, but I can't see the graph. So what I'm going to do is I'm going to zoom in kind of tight between -2 and 2 in the x direction, and I'm going to try to adjust the increment of x and see if that helps. And so as I zoom in like that, you could see that in the y direction that I had higher y values than originally. What we see here is that the curve literally, it's almost a corner when you look at it. So because of the behavior of the graph, because the corresponding y values as you approach true grows so quickly and approaches positive infinity so quickly, the graph screen, the pixels on the screen can't literally represent the data accurately. And so if I plugged in like 3, like 1.999 like that, the y value is already off the screen at 158. So that's a technology issue. The calculator can calculate the value, which is why we can't just look at the graph. We have to know the material, we have to understand it, and we have to be able to manipulate the technology to give us the answers we need. If we originally just looked at it, we might say that the maximum y value was 4 or 5, depending on whatever parameter we had set in the calculator. Now what I did do while I was rambling on there was I plugged in x equals 0, and it did yield 1/2, and based on the graph, that's the minimum value. So this function did not have a maximum value because it approached infinity, but it did have a minimum value at x equals 0, which was y equals 1/2. Now the way that I could prove that analytically is I just need to pick a number that's a little bit below and a little bit above 0 for x. In other words, if I evaluate f prime at -1 and f prime at +1, that'll tell me what the slope is. And so if the slope is positive, that means the graph is increasing. If the slope is negative, that means that the original function is decreasing. So the behavior of f prime can actually tell me kind of the curvature of the graph itself of f. And so that's how we get that smiley face. The smiley face comes from the fact that we start off with a negative slope that becomes less and less negative slope, and then when x equals 0, the slope is 0, and then from there it changes. So I go from a negative slope to a positive slope, which is indicative of a minimum value as opposed to a maximum value. And so when we plug that in and we look at the original function, f prime of x, that basically tells me if we're increasing or decreasing. So I'm going to plug those values in. Now an easy way to do that is to just plug it into your graphing calculator and look at the graph of f prime and then plug in or trace the corresponding x values like -1 or 1. And that will tell us if it's positive or negative. So a lot of times we're not interested in whether or not it is the value, we're just interested if it's positive or negative. And so if I plug in the green line is the green is f prime, so f is in red and green is f prime, and so at -1 here I see that f prime is negative, which means my slope is decreasing, And then at 0, it's 0, and then when f prime of 1 is evaluated, I get a corresponding y value. And that just means that f prime goes from negative to positive, which means that the slope comes down, it's decreasing. So the original function decreases and then increases after the critical point. So because it changes in that way, it's a minimum. If we went from positive to negative, then it would be a maximum. And so this is all done analytically, numerically, algebraically, and the graph supports that. So you will be required to know how to do it algebraically, analytically, but it is nice to look at the graph and see what the answer is. Does anyone have any questions?